Hello everybody, this is Dr. Rahil, and today we are going to start chapter number 10. Previously we have studied chapter number 9, which was about the main memory, and we have seen several schemes to manage the main memory. There are mainly two categories. We manage the main memory, and the contiguous memory allocation and the non-contiguous memory allocation. And the contiguous memory allocation, we have seen several techniques. In non-contiguous memory allocation, we have also seen several techniques. In all aspects of the memory allocation, we know that we always uh, loaded the entire process into the main memory. While for example, if we have if we see an example, let's say if I have a process 1 here, right, P1, and it may be like that, and P2. Okay, we have P2. Now we have a main memory here. Now operating system is loaded here, and the P1, the 3 pages of P1 are loaded into the main memory, right, and the 3 pages of maybe P2 are loaded into the main memory, right. So these two processes are actually available in the main memory. Now for example, if a third process has arrived, if process 3 has arrived and it has also 3 pages, then where it should go, right? So we can say that degree of multi-programming is very limited, right? Degree of multi-processing is very limited here, right? Very limited with the previous approaches. Whatever we have seen paging, segmentation. Sorry, we have not seen segmentation, but paging and different type of other schemes we have seen. So the degree of multiple processing is very limited in the previous approaches. Now the operating system has one functionality of virtual memory, which is actually managed by operating system. Okay, which is actually managed by operating system itself. This is, as the term suggests, it's a virtual memory. It's not a physically existing memory, right? So this is, we can say that more than function, more than memory, it's a function. It's an algorithmic way to organize or to manage the memory in a way so that the degree of multiple programming can also be improved, right? And also the fastest access and maximum CPU utilization can be done. So I hope you are clear until now, but later on we will be going through the chapter. Several concepts and things will be coming, and we will be getting much more richer experience of the virtual memory. Now the first of all, we will see the background of the study, what is virtual memory, and how it actually what are terms, and how actually we come to the conclusion that we have to use a virtual memory rather than the entire physical memory. So and this is all about the background study of the virtual memory. And then we will see demand paging, one of the algorithm, a very popular and very basic algorithm of the virtual memory, that how actually pages are being organized in a system for access, right? So demand paging is the algorithm. And then copy and write, this is about the child and parent processes, where we always use fork system call. We know that we use fork system call to generate a child process, right, from a parent process. So also we see that parent process and child process both sometimes always have the same copy of the information into them, right? For example, child process has copy of shared libraries and data structures and everything. Also the parent process has copy of data structures and shared libraries, everything is. So these both are having extra burden on the main memory if these two processes are loaded into the main memory. Okay, so we'll see how this copy and write actually manages these two. And then there's an algorithm, there's an other thing, which is allocation of frames and page replacement. Allocation of frames and page replacement is actually these two are actually the concepts used together. Okay, allocation of page means that how many number of pages should be allocated to a process, and the page replacement, that if a process has exceeded its limit or has reached its limit of pages, then how to replace the pages. The replacement, we know that from memory from secondary memory to main memory is always achieved by swapping, right? We know that. So how the swapping is actually works in the page replacement, in this concept. Okay, and also in the end we will see the thrashing. Thrashing is actually a limit of a system, that how much degree of multiple processing can be afforded. Now a system cannot execute maybe 200 processes, right? Or maybe 300 processes, or maybe 50 processes. The system can only execute a certain number of processes in multiple way, right, in concurrent way. So we'll be seeing the thrashing here, the concept of limit of the CPU for multiple processing. Starting from the background, we know that there are several routines, there are several data structures, and several methods which we don't use so often, and sometimes we don't use them for longer. For example, if we see MS Word or MS Office or any suite, any of the application from the Office suite, then there are several options we don't use. For example, if you see PowerPoint, then the transition and the animation and sometimes master slide, we don't use these options so oftenly, right? If you go to the MS Word, then we know that table of content, styles, and maybe printer function, we don't use these methods oftenly. So if we load entire MS Word into our system and entire PowerPoint into our system, then this will bring an overhead of unusual routines. We know that error code is also a part of program, which is always there, but it is rarely used. So it is also an overhead over the main memory. For example, if a process is loaded into the main memory and it has error code and some unusual routines, and it is maybe occupying 50 pages of your 50 frames of your main memory, then it can be squeezed to only 20 pages by removing those unusual routines. Only the functional, only the core code which is used to load the program or execute the program is required by a process, right? So entire program code not needed at the same time. We know that if it is needed, it can be requested, and I will tell you how the request actually goes to the system. And then consider CPU. Whatever process we have seen, whatever methods we have seen, now consider a way that if you don't load entire program into the system, so what happens that even the degree of multiple processes will increase, and CPU utilization will also increase, and the throughput may also increase. Okay, so this is what the background, and the virtual memory is the separation of logical memory from the physical memory. Now this virtual memory is actually a logical space, is actually a logical algorithmic way, not a physical memory, right? So we can separate this, we say that it is different from the physical memory. Okay, and only part of program need to be in memory for execution. Logical address space can therefore be much larger than the physical space. For example, if we see virtual memory space here, now if this is a virtual memory and this is a physical memory, then we can know that the virtual memory is this main memory. Okay, a main memory or physical memory, and this is, we say that, storage. Okay, actually virtual memory belongs to this secondary storage, but and it's a part of operating system also, and the management is actually the part of operating system, virtual memory management. Okay, so we know that we the the main memory is very limited in size. Sometimes we have 4 GB RAM, or maybe 8 GB, or maybe 16 GB RAM. We cannot increase this, and even if we increase, the system does not give us the enough performance as we expect. So the virtual memory takes place here, which actually increases the performance of a system by efficiently utilizing this memory space, the fast memory space. Okay, so only a part of how it actually achieve this goal, only a part of program is loaded into the main memory for execution, and logical address space can therefore be much larger than the physical memory space. We know that this is logical or maybe virtual memory space. This is much larger than the physical memory space. For example, if this is 4 GB, this might be 20 GB, or maybe 16 GB, right, or maybe 16 GB. It's okay, right? This is always larger, so virtual memory space is always larger, and allows address spaces to be shared by several processes. I have already given you an example of child and parent process, where the child and parent process previously they actually occupy the same resources, the copy of same resources separately, but now what we can do, that we can actually share those common routines and those common data structure in between two processes, parent and child processes, or maybe different processes. Okay, and allow more efficient process creation, more programs run concurrently, and less IO needed to load or swap the processes. Okay, because in previous approaches, what happened, that for example, I'm on this third point, right, and then on the last point. For example, if this is the main memory, this is operating system, and we have only capacity of 3 pages, let's say, and a process has come, let's say P8, and it has 3 pages. This process is accommodated here. Okay, this process might have priority of 5, right, and another process, maybe process number 10, has come and it has a priority of 1. Okay, so this process is also only this process might have only 2 pages, right, to write here, but there is no space. So what will happen, this process, the low priority task, the low priority process, will be removed from this main memory, and the new process would be swept in. So this process will be swept out, and this will be swept in, and this will be swept out. Okay, so it means that for allocating these a process, we need to perform swap operation on the entire process, but not only the page, not on the single page, but on entire process. So by utilizing the approach of virtual memory, we can reduce this burden from the from the main memory, or from this system. That's why the system performance would also increase. Now, virtual memory address space, the logical view of how process is stored in the memory. Now usually we have seen that the addresses are started at 0 in the contiguous memory allocation until the end of the memory, goes out until the end of memory, and this is actually an organization of physical memory. In the physical memory, we have pages, and we have pages on the CPU side, and on the memory side we have frames, and memory management unit is responsible for mapping in between pages and the frames. And so this is what actually the physical memory address space, but in the logical memory address space, this is not this is almost the same, and but the memory the physical memory is replaced with the logical memory here, and virtual memory can be implemented by via demand paging. Now what's demand paging? And the second approach is demand segmentation. As we have not seen the segmentation in previous chapter, so we will skip this segmentation here also, and we will be covering only the very important topics in this chapter. So you can see an overview of how the virtual memory is actually available in our system. We can see that virtual memory is also organized into the pages, the same fixed size of pages, which are fixed size of pages, right, which are actually equal to the frames. So this is the memory, and if a page is looked over here, and it can be found over here, right? If a page, let's say page maybe 2 is looked over here, which is allocated over this location, then it's fine. But if page number n, let's say page n or page n, or maybe whatever page number n is, we are looking for page number n, and it is not found in here, then it will be searched from the backing store or maybe secondary storage. Okay, so this is an overview. We have a virtual memory and a physical memory, memory mapping, and the backing store. Previously we have virtual memory very small, which was coming from the CPU, and logical memory, right, logical addresses from the logical memory, and now we have a virtual memory here, which is replacing that concept. Okay, now virtual address space. There's an example given here. We know that in every process we have these parameters, like we have stack, we have heap, we have data, and we have code. Now these all from these all we have stack and heap, which are flexible. Now for suppose if we need some data on stack, then stack will grow, right? Stack will grow its size. And if we have some thing to do with heap, then heap will grow. And these two are shrinkable or growable, right? These grow up or grow down, right? These two, stack and heap. And now this portion, this memory portion, is known as hole. Now for suppose if a process is loaded and this hole is larger, then isn't that wastage? Yes, it is wastage. So using sparse, by enabling sparse addressing space, the left holes are actually dynamically linked with the libraries required. Now we know that these are in these holes, we most of the times we fill in the libraries and the data structures. So these libraries are actually dynamically allocated, and this hole is not always occupied. So sparse addressing, this is called as sparse addressing. Okay, we can see here that these are two processes, these are both sharing the same libraries, so why not why to actually allocate them different libraries? And we have a shared library, as maybe we have another process here, right, which is actually occupied with this hole, right? And we have a stack here, and we have heap here, data, and code. So we can see that this shared space is actually shared in between 2 or 3 processes, and this is much more efficient than for example, this shared library might be of 3 pages, page 1, 2 and 3, and 1, 2 and 3, 1, 2 and 3, 1, 2 and 3. So if we allocate them independently, then this will be a 9-page long library, which is actually same shared into the 3 processes, right? So only 3 pages, we only use 3 pages from the memory here. Demand paging is actually a lazy swapper, lazy page loader. What happens that could only bring entire, previously we were bringing entire process into the memory at the load time, but now what will happen that we will only load the pages which are required. Okay, bring a page into the memory only when it is needed. Okay, So this is what the demand paging. We don't bring the extra pages, all the unusual or error codes, or maybe very rarely used routines into the memory. We only bring the required or only needed pages into the memory, and if it is not needed, we don't bring it. Now how this is managed, similar to paging system with the sweeping, right? It is managed. The pages are swept into the memory and swept out of the memory. If the page is found, for example, if this is a process one, oh sorry, this is, if this is a memory and this is a process, it might have several pages, and let's say this page and this page, these two pages are necessary for execution, then only these two pages will be loaded either in contiguous or uncontiguous manner. We don't care about that, but these two pages are actually loaded into the memory. Basically, if we are talking about the paging, then these can be, this is actually non-contiguous. Okay, but let's say these are accidentally placed into the contiguous manner. Okay, so these two pages are written over here, are brought over the main memory from the process 1. Now for example, if the third page is needed, and then it will be swept in from here, right? And if the fourth page is needed, then it will be swept in here. Okay, so all the pages which are needed, once they are needed, then only they are brought into the memory. If the need is finished, then it will be again swept out to the secondary storage, okay, or to the virtual memory. Okay, so swept out, and this is swept in operation. So similarly to the paging system, sweeping is actually done over here, and page is needed. Okay, if the page is found into the main memory, then it is a valid page. If page is not found in the main memory, then it is a invalid memory. For example, if this page is loaded into the memory and another a CPU IO generate for access of this page, okay, and it is found, if it generates an IO for this page, and for suppose this is not loaded into the main memory, then what will happen, there's an invalid, this is invalid location. Okay, this is an invalid location. Then what will happen, a trape will be generated to the secondary storage for this page access, and this page is returned to here. Okay, then this page is brought to here. Once it is brought to here, then the process will resume from here. This process can this diagram is ugly over here, but it's just for giving you a glance of how demand paging actually works. The neat and clean diagram you can see in the next slides. So the invalid reference, if the reference here is invalid, then the process is aborted or maybe paused, right? That or maybe paused for some time. Okay, and the new page which was requested is claimed from the secondary storage, and the invalid means that not in memory, and if it is not in memory, then bring it to the memory. Okay, so the lazy sweeper never sweeps a page into the memory unless the page will be needed. This is a good thing, the lazy sweeper, and sweeper that deals with the pages is a pager. So this is just as we should know that how actually demand paging works. So demand paging is working is like that. Only the pages which are in demand are brought into the memory, and those which are not into demand are swept out. So we can see here the sweep in and sweep out function. as in the previous slides. I have already shown you that in previously we have entire process to swipe in or entire process to swipe out, but in this way, in this we only swipe with the pages, not with the processes. Okay, now for example here we have 4 pages of process A and 3 pages of process B. Then on on arrival of a priority task, the entire process is swept out and the entire new process is swept in. This is not actually done in the demand paging. Okay, the basic concepts with the swiping page, I guess, which page will be used before swiping out again. Actually, swiping out a page is not